So this video, I am only going to do one example, and I'm going to focus this video on an example that is probably one of the most common examples of what you'll see either on an AP test or even in Delta Math. I call it the ladder example, but you could actually call it like a triangle example. And the idea is when you're looking at the sides of a triangle, as I change one side, it's going to change another. So here's what I mean by that in terms of a ladder. So again, I have horrible artistic ability, but this is what we're going to picture. So we've got this wall here. Let's call that a wall or a building. And we've got a ladder, which I'm not even going to try to draw a ladder like that, that's leaning up against the wall. And here's the ground. So if you kind of picture in your head this ladder that is leaning up against the side of a wall or a side of a building, and all of a sudden the ladder starts to collapse. And what's happening with this ladder when it collapses is the top part of the ladder starts to slide down the wall. So picture it as kind of just skimming along that wall. And as that happens, the base of the ladder is sliding away from the wall. So we have those two things that are changing, and the rate at which they're changing is related. So again, it's called a related rate. Now, the ladder in this problem is not changing, and you will have some triangle problems where all three sides of the triangle are changing, and we'll talk a little bit more about that in detail as we go through. But in this example, it's a ladder. It's not a ladder that's going to get shorter. It's a 25-foot ladder. So that is going to remain a constant. So that's like the hypotenuse of my triangle. So I need to assign some variables here. You can use any variables you want. I've had students use like G for ground or H for height or W for wall. I'm going to just use X for the piece that runs horizontally, and I'm going to use Y for the piece that runs vertically. And what I have as the X value is changing, we're going to call that dx dt. And that's the piece that's going to be talking about how fast that ladder is going away from the wall along the ground. And as this one is changing, as it's sliding down, we're going to call that rate dy dt. So here's what they tell us. They tell us that it is sliding away from the ladder at a rate of 15 feet per second. So that is going to be your dx dt, because that's how far that is sliding. And since that distance is increasing, it's a positive rate because the base of the ladder is going further and further away. And our job is to figure out how fast is it sliding down the wall. That's going to be your dy dt, specifically when it gets to be 7 feet from the ground. So that's kind of setting up my picture again. Sorry about the not great artwork. So first I need an equation that relates these quantities. So I've got the X, I've got the Y, and I do have the ladder length. So hopefully you look at this and say, oh, well, that's a triangle. It's a Pythagorean theorem. And that's exactly what's going on here. So I call them often ladder problems, but you actually might be better served to think of them as Pythagorean problems. So I have X squared plus Y squared equals 25 squared. That's the way I can relate those three quantities, your X, your Y, and your, in this case, 25. Now you'll notice I did not put a variable for the 25 because that ladder length is not changing. If it was, if the hypotenuse was changing, then I need to put a letter there too. And often I use like C for the hypotenuse or H for the hypotenuse. So you're going to take the derivative. So the derivative of X squared is going to be 2X dx dt. The derivative, that's an X, it's a messy X. The derivative of Y squared is going to be 2Y dy dt. And the derivative of 25 squared is just 0 because 25 is a constant. And when I square it, it's still a constant. And this should make sense because there is no change in the ladder length. That's why you're getting a 0 when you derive that, because the ladder's not changing. If you want, you can cancel the 2's. Often I do that just so it's working with some smaller numbers. And then you can plug in what you know. So I know that my dx dt is 15, so I'm going to put that right there. I know that y is 7. I know that dy dt is what I'm looking for. Finally, I need to figure out what x is. And x is also going to be found with the Pythagorean theorem. I know I'm specifically looking when this side is 7, this side is 25. If I'm missing a leg, and that's what I'm missing here, I can quickly do a Pythagorean theorem, do 25 squared minus 7 squared under the square root. I can grab a calculator if I need it. I think this one works out really nicely. Let's see. So square root of 25 squared minus 7 squared is 24. So that's my x value. So I'm going to put that in. and that equals 0. So I'm going to multiply the 24 by the 15 and subtract that to the other side. So multiply that by 15, I get 360. So I'm going to subtract 360 over here, and that will equal 7 dy dt. And then I'm going to divide by 7, and I do not believe that reduces. So I'm just going to leave it as a fraction. If you want to write it as a decimal, that's fine. Just make sure you go 3 decimal places. Now my unit is how it's sliding down the wall, down the wall. So that is just a distance change. So that's going to be feet per second. So let's talk about the fact that it's negative, because the negative shouldn't surprise you. There's actually two reasons it's negative. One is kind of more of a physics point of view, the idea that it's sliding downward, and again, that negative is the direction. The other reason it's negative is that distance is actually getting smaller. As the top of the ladder slides further and further down the wall, the distance from the top of the ladder to the ground is shrinking. So that's another reason why it makes sense that you have a negative answer. So that is my ladder problem. And I can do this with any triangle where I have sides changing. I can have either the legs changing, I can have the legs changing and the hypotenuse changing. Now, if that's the case, I'll just kind of add a little supplement to this. If you have all three sides changing, then you need to make sure that when you set up your equation, you put a variable for everything. So you'll have an x squared plus y squared equals whatever you want to call the hypotenuse. I often use c squared. And so when you take the derivative, you're going to have a dx dt, a dy dt, and a dc dt to go through. So that is your ladder problem. Most common question. There's actually a whole section on Delta Math about triangular related rates that you'll use a lot of this for.